Greetings viewers, in this video we'll do Cambridge A-Level Further Maths, syllabus code 9231. This is Further Pure Paper 2 and variant 4 from the May June 2025 series. Let's crack on with question 1. And they're giving us a system of linear equations here with 3 variables and a constant k here. So we want to prove that or we want to find the values of k for which this system of equation does not have a unique solution. So remember the condition for a system of linear equations to not have a unique solution is for when the determinant of the matrix is equals to 0, right? So if you can recall, for no unique solution, the determinant of the matrix must be equals to 0. And what matrix we are talking about is we can make this system of equation into this type of matrix, which this is come from the matrix algebra, the xyz multiply, the matrix multiplication. You should know this by now. And so to do the determinant also, remember the procedure where we want to find the determinant of this entire 3x3 matrix. What we have to do, there's a few different ways of doing this. You can just memorize by formula, but I prefer to do it this way. We look at this constant, or we look at the first row, first column. We eliminate this first row and first column, and therefore we take the digit that we have selected, which 1, and we multiply by the determinant of the leftover 2x2 matrix. And we repeat this for the second column of the first row, which we get the digit 2. We eliminate the row and the column, and we are left with, in this case we have to minus the 2 because of the power, the power of the matrix there. So the left over the 2x2 matrix, taking the determinant. So that's the determinant. Finally, we look at the number 3 here, the third column, and we eliminate this row and column. So we have adding 3 of the determinant of k5, 7, 2k. So and if you can recall also that for a 2x2 matrix, the determinant is found by cross multiplying like this. So multiplying downwards, remember that is a positive, right? And then multiplying upwards, there is a negative. And we equate this entire equation to 0. So I'll go ahead and do the computation here. Okay, after you finish doing the simplification, you should be able to get a quadratic in terms of k squared minus 5k plus 6, from which you are not 6, 6 is supposed to be 4. Okay, 4. Yeah, for which you should be able to factorize into k minus 1, k minus 4, and therefore you have two values of k for which this system of equations does not have a unique solution. So these are the two values of k. Okay, for question B, given now that k equals to 1, show that the system of equations in part A is consistent. Interpret this situation geometrically. So let's recall what this means is that consistent means they have it's solvable. But for consistent, we also have two cases for which where it is having a determined or a unique solution, or also the undetermined case where we have a larger number of unknowns than the linearly independent equations. So first, let's state we have three unknowns, right? Three unknowns which are x, y, and z. And I'll copy down all the equations for which k equals 1 first. Right, so we need to try and prove that, or we need to try and find how many linearly independent equations there are. So we're going to do some elimination here. So first of all, we can take probably the second minus the first. Yeah, the second equation minus the first equation, you should be able to get 3y plus 3z equals to 1. And we also can take probably the third equation minus the first equation. We can eliminate the y there. So we have 6x plus 6z equals to 2, for which we simplify into 3x plus 3z equals to 1. Okay, and from these two equations, we can also solve or we can eliminate z, right? So we eliminate, once we eliminate z, then yeah, we just end up with x equals to y. So z is a linearly independent by its own. Okay, so z has its own solution. We don't know what that is, and we have another linearly independent equation here, which is x minus y equals to 0. So actually, we only have two linearly independent equations. So we only have or two pieces of information that's given to us, but we have three unknowns. So therefore, we have proven that there is a solution where x equals y, and then there's one more or we can use this information to solve into another or back into the original equations, but this is still unspecified, or there's still one degree of freedom. We call this one degree of freedom that is left unknown. So there will be we call this an undetermined equation, or a system of linear equation, right? So it is consistent, but it's undetermined, or there's still varying degrees of freedom. So we also want to interpret this situation geometrically. What we can observe here is that it's a x, y, and z situation, so it's definitely a 3D space. And x, y, z, that is the equation of a plane, right? X plus y plus z. And we also know that there is this x equals to y, and this is where the or arbitrary, what we call the unspecified variable comes in. So the solution lies along where these three planes meet, and there is infinite or an infinite number of solutions where z is equals to something. So the geometric interpretation will be that these three planes, they meet along a line. So there is an infinite amount of solutions to this system of equations, unless we specify one more piece of information, so that there's 0 degrees of freedom. Okay, so this is a interesting topic for, I guess, computational stuff. So if we're going into computer science or simulation stuff, so simulation stuff, we need to or specify a lot of different variables, so that those software can actually solve the equations, right? So if you develop the software, you're gonna have to know how this works. Yeah, so that's question one. So stay tuned, we'll complete the rest of the paper soon. And thank you for watching.